some sun coming on my face. It's not disturbing. But you can't actually see me. You're looking at the slides. That's fine.
Yes, Jacob, I think you can start the introduction.
Okay. Hello, everybody. It's a pleasure for me to introduce Alon Halevy, who is a quite famous person in artificial intelligence in general and machine learning domain in particular, and who is currently a director of AI at Facebook. And he had quite practical experience of using different AI technologies when he was with Google and when he ran his own labs. And we're going to hear quite interesting perspective of symbolic AI in machine learning world where we all live today. So let me give floor to Alon, and thank you for joining us, Alon.
Thank you for inviting me, Jacob. It's really good to be here. I'm in California. It's 9 o'clock in the morning. Thank you for everybody who's like in Europe and it's the end of their day, and I understand it's less convenient. So first of all, I want to acknowledge some of the co-authors of the work that I'm going to be talking about today. These are James Thorne, who's finishing his PhD at Cambridge, Majid and Marzi at Facebook, Fabrizio Silvestri, who used to be at Facebook and now is a professor at La Sapienza. Go and study with him if you can. And Sebastian Rydell, who's everywhere. He's at Facebook. He's at University College London. So as Jacob said, I come from the world of symbolic AI. Okay. Not only that, I did my initial work on knowledge representation, and then I moved even further to database management, and I've actually spent many years working on certain aspects of data modeling and data processing. And now, for the last 2 years, I am sitting in Facebook AI in one of the teams at Facebook AI, and it's a very different world. In Facebook, everything is about machine learning. So the first, and I'll be honest, it's not, for a symbolic guy who's, I should say, coming from the symbolic AI background, I'm drinking the Kool-Aid. Okay, so I love all the machine learning stuff that is going on, and we're trying to leverage it as much as we can. But it's these two worlds, when they come together, presents many opportunities and many challenges. So I'm going to start out by talking a little bit about what are the data that we actually have, okay, and what are the questions that we want to answer or insights that we want to get from this data, and then we'll try to think about how to do that. And then if you look at the dominant paradigm today in machine learning labs, I think there is a mismatch between actually getting insights from data and the typical machine learning paradigm, which is let's get training data and training model to answer one particular question. So I'm going to talk a little bit about that, and I'm going to raise more questions than answers. And then I'm going to spend hopefully most of the time on one possible approach to this, which is neural databases, which is work that I've done with all the people that I just mentioned. And if there are any questions in the meantime, in the middle, please, I know it's Zoom and it's hard to do, but do ask. Okay, so let's start from what is the data, and that's where you sort of get your first midlife crisis. So we're talking about social media, right? So the data that we have is generated by users, any users anywhere in the world. I have on the slide here, I could put an example of a social media post, but any post that I would put would generate too much trouble with somebody. So just assume it's a social media post. It can be Facebook, it can be Twitter, it can be Reddit, whatever. So the data is generated by users. By nature, it has no schema. You're not even allowed to ask a question. Okay. Sometimes in the database world, we talk about, is there going to be some schema? You know, some cases where there's not going to be schema, but can we create schema? You're not even allowed to ask the question. There's no schema here. Okay. The data is most of it is in text. Okay. But there's also multimodal data. So people put images and videos, and a lot of the semantics, a lot of the meaning of what they're trying to convey is in those modalities and in the combination of the two or the three. The data is very short, so people don't write terribly long posts on social media, and because of that, the context is key. So you sort of need to know what's going on either in the world or in their lives, or have a lot of what we call common sense knowledge to really understand what is the meaning of the data. And it's short-lived. So, you know, a post from 2 weeks ago may or may not be relevant today, probably not. The other thing is, you know, in databases and in knowledge representation, we typically try to represent things that have a truth value. It's either true or not true, or true with certain probability. Here, it's a lot of this data is subjective. This is my opinion. Okay, it's not about true or not. It's about this is what I think, and c'est la vie. So that's the data. Okay, so social media posts is sort of the raw data. You can also imagine data that is basically short textual sentences, like, you know, John lives in Canada with his brother. Now, I highlight that kind of data for two reasons. One is you can, you know, sometimes that is the data that is in the social media post, and I'm also looking at applications where you're talking with an agent, like a Google Home or you know, Echo or something like that, and you're actually saying, you're actually telling the assistant things that you want the assistant to remember. And also in those cases, you don't have a schema, and you talk the way you want to talk, and you may not say the same thing using the same words twice. So that's the kind of data that we have. Now let's talk about the questions we want to answer. And why am I the questions? Okay, so there's a huge field. So there are two sets of questions: the bad and the good. Bad meaning trying to remove bad content. So integrity is a term that is used in order to refer to the types of content that violate the policies of social media platforms. So the big examples of that are hate speech. You're not supposed to say anything hateful towards specific populations on social media. Bullying, you're not supposed to promote violence. You're not supposed to encourage people to commit suicide. You're not supposed to sell illegal items. These are policies that are written in various places, and every company has their own thing. And we have teams in place that build huge pipelines in order to try to minimize the amount of violating content on the social network. Okay, so the one possible question that you may want to ask is, I have a social media post, is there hate speech here? In other words, given the policy that is written down, you're not supposed to dehumanize people who belong to population X. Is there a violation here? Or the other kind of violation that gets a lot of attention is misinformation. Obviously, we don't want to have or spread misinformation. If you want to know more about this topic of integrity, which is actually fascinating, and sort of like the solutions that people have developed to integrity are a true tour de force of AI and AI today. So there's a survey, an archive that's going to come, a shorter version is going to come out on the CACM pretty soon. So those are the kinds of questions that we're trying to ask about this data. Does this data violate a policy? But we also want to go a little bit more specific, right? So, for example, we want to find posts that claim that X, where X is a free variable, it could be you choose your favorite X, okay, won the election, and which election is also part of the context. Or find me posts that claim that some Y, some cure cures COVID. Okay, so this is a little bit different than does this contain misinformation. This is a little more proactive. I already know that people are trying to propagate false information, and I sort of know what are the kinds of information or misinformation they're trying to propagate, so I can be more proactive in my query. Okay. Or another kind of question that is, again, we're getting into more detail here. When you talk about hate speech, you in order for something to be hate speech, you need to it needs to target a protected population. Protected population can be by race, by disability, by, there are a bunch of criteria. And so in order to be able to mark something as hate speech, you need to identify exactly which protected group is being targeted in this post. So now it's not just about is this hate speech or not, it's who exactly is being targeted in this post. Now I'm highlighting these things because as we're going to see in a moment, this changes the paradigm that we need to use in order to answer these questions. Okay, so these are the bad questions, or questions looking for bad. But there's a lot of good stuff we want to do, right? So one of the nice things about social networks is you have the collective intelligence of all of your friends, and sometimes you actually want to leverage that in order for your own good. So maybe you're going to London and you want to know, okay, which of my friends lives in London? Maybe I'll get in touch with them. This is pre-COVID. Today we don't go anywhere. I'm planning a trip to Costa Rica. Have any of my friends gone to Costa Rica and recommended hotels or attractions or stuff like that? That's also pre-COVID. We don't go to Costa Rica anymore. Actually, we do. I think it's safe. And this is very COVID. I'm going to spend all my time watching Netflix. And so what do my friends think about, say, the series, The Crown? So the information is there, but you want to extract it in a way that is actionable for you. So now let's look for a second at what are the possible ways to answer these questions. So what we do for hate speech, for example, and we do for all these violations, and I should say there are about more than 50 types of violations that you see on social networks. Okay, hate speech is just like hate speech and misinformation are like the big two that get most traffic and most attention. So what we do today is we build a model. We get a bunch of annotations of posts, and we have people who are trained to understand the policies of hate speech or bullying or whatever, and so we train the model, and it's a deep neural net model with multi-modal, very fancy, and we come back saying yes or no, or we come back saying giving a number, and if that number is above a certain threshold, we remove the content. If it's below one threshold but still above another, then we look at we give it to a human or a few humans to decide. Misinformation is a little different for two reasons. One is, Facebook or other social networks don't want to decide what's true in the world and what isn't. So when something is suspected to be in misinformation, that post gets sent to third-party fact checkers. And these fact checkers are, first of all, they know what they're talking about. So that maybe they're trained in medicine, so they know, what might be a medical false information, or maybe they're steeped in politics, so they know, some of the political events going on, and they can go and find proof for something being true or not. Now, those obviously, as you can imagine, these pipelines are very, very thin. They don't get that many posts rated on a daily basis. So what the social network does do is it does similarity search. So when a post comes in and and it's deemed to be very, very similar to something that has already been debunked as false or true, then we will action on it. So if it's very similar to something that was false, then it'll be removed. Okay, so that's another tool in our toolbox. It's similarity search. Which protected group is being targeted in this post? That's where it starts getting tricky, right? We don't, because there are multiple protected groups, and yeah, you can build a model for each one of them, but that's not terribly effective to do. For the more positive questions, there's an entire field in the natural language community called question answering. And basically there you have a relatively short piece of text. You can ask a question in natural language, feed it to a transformer and pray. And actually these transformers are really, really impressive. So that works a lot of the time. So here's one of the main points I want to make in this talk, which is if you look at, let's go back a second, right? If you go to the world of say data warehousing, right? What is a data warehouse? A data warehouse does a lot of work up front in order to answer certain questions very, very efficiently. And the reason we do that is because we know that that question is going to be asked so many times that it's worthwhile to make the investment to bring all the data together in the most efficient way in order to support these very frequent queries. Okay. When you do other kinds of decision support, you want to be more flexible. You want to be able to ask a query such as, which of my employees are making more than 100K. Sorry, I'm taking a boring example, and then say, hold it. Now I'm looking at this. Let me partition by state. And then, so basically I'm changing the query on the fly in order to get more insights. So, so the same thing is really happening in the world of machine learning meets data needs, right? So the example of building a model for hate speech is like building a database, a data warehouse with an optimized view for a particular question. Okay, so so I'm spending a lot of effort to develop a model that is going to answer only one question: is this hate speech or not? And there's nothing wrong with that, right? So that's on the left side of the spectrum. On the right side of the spectrum, what is our alternative? Our alternative is to try to extract from the data triples, if you want, into some graph structure that was predetermined in advance. And then once you have the data in that graph structure, you can use whatever graph query language you want, and you can do whatever you want. So we have, on the one side, we have data flexible, because now you can, obviously when you're extracting stuff into a graph, you're losing a lot of information. When you're building a model that goes directly to the raw data, you can, anything in the actual data gets taken into consideration. And so these are the paradigms that we have. And now we have a bunch of things in the middle. So for example, the question answering work in the NLP community is sort of trying to say, okay, I'm going to be able to ask you a particular question that I can change. I can ask you one question now and another question in 5 minutes. But those models, while powerful, they work on really small data. There are attempts in the machine learning world called zero or few shot learning, which is, okay, I have this pre-trained model, and I'm not going to spend a lot of time training for this new task. I'm just going to use a few examples in order to adapt or to fine-tune this model for this new task. On the other side of the spectrum, we have what has been called common sense knowledge graphs. I'm referring here to some of the work that came out of AI2, where you have graphs that the edges have very clear semantics. For example, if X does something to Y, then Y will feel annoyed or something like that. So that's the semantic of the edge, but the stuff in the nodes are basically phrases. They can be anything in natural language. So that's really interesting because the nodes can be anything, the edges have semantics. And that's, I actually really like that work. I think one, people talk about system 1 and system 2 reasoning. System 1 is sort of the intuitive, taking everything into consideration. And system 2 is the more deliberate, hold it, I need to calculate something or make it a few steps of reasoning here. So if you think about it, right, the machine learning models are closer to the system 1, and when you want to do system 2 type reasoning with more, intricate reasoning, you have to go back to the symbolic declarative world. But I think the real issue has to do with decomposability. So when you decompose, so when I ask you, is this hate speech or not? I'm not decomposing the query. I just want an answer to that very, very broad question. When I'm asking you, I need to know whether this is hate speech, but I also need to know what is the target group, what is the group that is targeted, and what is we call it the attack vector. There are different ways of being bad, okay? So the attack vector is like, an attack vector could be something like dehumanizing people. So I need to know who is targeted, and I need to know what is the attack vector. So now what I've done is I've taken the hate speech query and I've decomposed it to 2 subqueries, okay? And that's where the paradigm breaks, right? I realize this is a little maybe vague, but when you take your query and you decompose it, all of a sudden your paradigm of building the model breaks, because now you need to be able to explain the answers to your subqueries. Okay, so and then you're supposed to you need to combine those using logical operators, right? So it's only hate speech if there is a protected group and if there is an attack vector. It's the conjunction of those two. And now, so in the lovely world of declarative AI, where you have some sort of representation or some sort of schema, decomposability is sort of clear, because you have the basic terms that you decided to put in your representation, and anything that is, combines them is, the decomposition is explicit, right? Your query is written in terms of conjunctions and unions and negation of these basic representational elements that you decided to put in there. But in the world of, of text and no schema, decomposability is a more subjective thing, right? Because I can talk about, one person can talk about more complex topics in a simple way, versus others might use the same thing, use a conjunction of terms. So my point is that the tension between these paradigms, between developing machine learning models as one big box versus trying to do something else, which I'll talk about in a minute, comes when you need to decompose, okay? And decomposing is important because, first of all, it's important for explainability. So we are not happy anymore when we just say this is hate speech. We need to explain to our users exactly why this is hate speech, or alternatively, why something that they thought is hate speech is actually not hate speech because it doesn't violate the policies. There's another question after that, which is why are your policies the way those are written? But that's a different issue. Okay. The other thing that happens is that policies do change very frequently because the world changes and people attack people in other ways. So if today, if Facebook wanted to, and we do this all the time, update the policy, then from between the time that we write down the policy and the time that we can enforce that policy using our AI systems, that lag is too long. What you'd like to happen is you write down the policy and boom, you get some sort of machine or you get some sort of algorithm that will be able to detect it very quickly. Okay, so taking this theme of decomposability, we can do two things, right? We can compose a query time. We can look at a query and say, okay, we will compose this into different building blocks, which we will then combine using logical operators. But the building blocks themselves, the leaves of your tree, if you want, we're gonna use the latest and greatest neural stuff to answer those. You know, an example of this work that from a couple of years ago is neural module networks, where the idea was, you know, to answer questions like, what is the color of the ball sitting on the green couch? Okay, so this is a complex question. Now you can, vision systems are good enough that they can identify a couch, they can figure out which couch is green, they can find the ball, and then they can actually tell you what the color of that ball is. But they can't do it in one fell swoop. You need to decompose that question into multiple questions that each one can be answered by a specific, you know, the vision system in its full power. So that's one possibility. Another possibility, which I'm not going to talk about today, but I would love to see more work on, is that the other side of the spectrum, the knowledge graphs that we build, become a little funkier, okay? And basically I'm thinking about graphs where the edges are, their semantics might be clear or might be subjective, or might correspond to a specific atomic machine learning decision. And similarly, the nodes might also be a little more vague. It may not be obvious that two different nodes actually correspond to different things. Maybe there's a little bit of messiness in those nodes, but still, I think it's possible to come up with some graphs that will enable you to get more complex answers out of this data. Okay, so now I'm going to talk. So now, now I'm going to talk a little about neural databases, which is one solution or one possible way to approach these problems in some contexts. Okay, so a neural database is basically, so now we're going to go back to these. So the database itself is, think of it as a set of sentences. So things like John lives in Canada with his brother, Mark was born in the US and lived there all his life, Bob moved to New Mexico in December last year, okay? And the query is also expressed in natural language. How many people live in the US? Who lives in North America? And you can see the answers if you actually think about it for a second. The answer to the first question is 2, and the answer to the second question is John, John's brother, Mark, and Bob. Okay, so this is so the point here is we're going to try to support database-like queries, but our data is not going to be tuples or triples or anything like that. Okay, it's going to be short natural language texts. Now you have to realize that for a database person to say we're gonna let go of schema, that's equivalent to like 5 midlife crises. Okay, it's not an easy thing to do, but given the amount of data out there that is just not sitting in any schematic form, it's a challenge that that we do need to face. So this I sort of motivated why to build a neural database already now, but the point is that databases are lovely, they're awesome, so are knowledge bases, but what goes in them is defined in advance. And in the setting that we're working in, and even in settings where database systems have been very successful, there's always a loss of information. There's always something that can't go into the database, or goes into the database but goes into a column which is text or image, and the information is not really fully captured in the questions that in the answers to the questions that we ask later. So we all know here that database schemas are hard to change. They lose information, and so we're trying to get the same idea of asking queries, but relaxing this assumption. Okay. So what we're going to do here is we're going to essentially use. So we're going to drink the Kool-Aid. Okay, we're going to say, let's see what the NLP world has to help us. Now, I should also mention we've done what in our current work we developed neural databases for text, but really there's no reason that this can't work for images and videos as well, because once as you'll see at the core of the system, you have a powerful machine learning model that that can work on text. It can also work on images and videos. We haven't done that yet. So what the idea here is we're going to have a set of facts that are written in English or whatever language you want. We're going to take the query. We're going to put them all together. Okay. We're going to feed them to a transformer. Okay, a big transformer, and we're going to let the transformer give us the answer. And we'll so the point here is we're going to train the transformer. We're going to fine tune the transformer to answer questions on relations that we're interested in. But the benefit at the end of the day is that I can say the same fact in multiple linguistic variations and still get the correct answers. So I don't need to a priori take my data and fit it into, remember exactly what is the schema and what it means. This is what I would think is a pretty big step forward. Now I should also say, don't expect neural databases to be running the database for your bank or your payroll in your company. That's not what they're intended for. They're intended for contexts where there's just no schema in advance, and you need to support anything that people are interested in. Okay, so then the question is, can we already do this? So as I said, there's been a lot of awesome work on question answering, especially say on Wikipedia. What they do there is you have a question, you somehow use an initial phase where you extract or you decide using a big index, what are the paragraphs in Wikipedia that that you're going to use. Okay, so you, in a very quick process, you find the relevant paragraphs, and then you take those paragraphs and you feed them into a more expensive computation that is done by a transformer, and you get your answer. Okay, and so we started by doing an experiment. We took the state-of-the-art transformers, and we trained it to answer certain queries. Okay, so on certain relations that we decided to train. And we took tiny databases because and this is the important point, right? That the transformers, because they are limited in the input that they can take, and because their computation is quadratic in the size of the input, this approach of using existing NLP methods can only work on really tiny databases, something like 50 facts or less than 1,000 tokens. And we did a bunch of experiments, and the colors in this graph are pretty cool. But the point is, there are two things that emerged from this experiment. One is that if you look at if you give the transformer the relevant facts, okay, in the input and with the query, transformers can do pretty amazing things. So they can do a join. They can figure out that two facts are actually contributing to the answer and give you the join. So the very and they can also do retrieval. So if I say, John moved to London, and I ask, where does John live? They will tell me that John lives in London. So fundamentally, they can attack the most the hardest problem, which is the linguistic variation and the need to combine facts in order to get to answer the question that you're asking. Now, that's, again, for a database person, that's mind-blowing, right? Because it's like these things are actually able to do the core operation that database or knowledge-based systems were built to do. But they don't scale, and they can't deal with because they can't scale, they can't look at large amounts of data, and therefore they can't do sums and aggregates. But even on small data, they don't understand things like counting. How many people live in London? They don't. They can't do that. So because of their limited encoder size, they're only limited to small databases. And because of that, you need to, the selection of the data that goes into the transformer is also a challenge. How do you know what to give it in order to get the right answer? And they're limited with when it comes to generalization and even numerical reasoning that database systems do as part of their bread and butter. So here is the proposed architecture. The other thing, let me actually spend two seconds on this slide. The fundamental difference between the work on question answering and the work in database or knowledge-based systems is that database systems fundamentally manipulate sets. So when a query comes to a database system, it says, okay, I'm going to break this down into a bunch of set-based operators. One will get a bunch of data from here, a bunch of data from here. Maybe it'll do a selection, maybe it'll do a join, maybe it'll do an aggregate at the end. But that's the way you're thinking about answering the query. In the QA work in NLP, that's not the paradigm. You're trying to answer one specific query, and if that means generating a set, then you're stuck. If it means that your answer is sitting somewhere in one paragraph or even two paragraphs on Wikipedia, then you're in luck. So there's a limitation to at least the way the NLP work is progressing right now. There's a limitation to how far it can go unless you start realizing that certain questions require manipulating sets as a first-class object. So here is the proposal, or here's the neural database architecture that we built. And again, this is a sort of a prototypical architecture, and I'm sure that many variations on this will be developed in the future. So you have the facts on the left-hand side. John works at Shell, and Sarah is a doctor, and Sarah married John. And now your query is, how many people's spouses are doctors? Okay, so the first stage in query processing is going to be what we call a support set generator. So the solution here is really simple, right? So we say that these very powerful transformers can only take small amount of data. So what do? You scale. So you have many copies of transformers, each one looking at small data. They're going to produce an intermediate answer, and then you're going to put it all together using the techniques that we know and love, like aggregation and union and what have you. Okay, so essentially you're giving the transformer just the right amount of facts to do what they want. And notice that some facts might have to go to multiple transformers. Okay, this is not a partition of your data. So the transformer itself, the operator, we call it a Neural SPJ. SPJ in the world of databases is select, project, join. It's sort of the basic operator basic set of operators that a database system does. It's where all the happiness happens. Okay, so this is going to be neural. We're not going to do it the database way. We're going to do it the neural way. Okay, so then if each one of these transformers, if each one of these Neural SPJ operators is going to get a small amount of data, then we need to precede that with some process that we call the support set generator that basically looks at the data in the database and creates these small sets, and each set is fed into one of these Neural SPJ operators. Okay, the Neural SPJ operator will actually produce a structured answer. Okay, it'll produce, and you'll see this in a moment, it'll produce an answer that then can be processed further by a more traditional database system. Okay, so let's talk for a second about support set generator. Remember, this is taking the entire database and saying which part of it is even relevant to this query, and of the data that is relevant, how do I give it to the different transformers? And so first of all, if you take a step back here, you realize that in many contexts, the semantics of the application already tell you what these support sets should be. So if you're looking at many posts on social media, usually a post can be a support set. Okay, it's small enough and we're usually not doing joins across multiple posts. Okay, when you look at user data, then even the user, him or herself, once you partition by user, then you're getting a set of data that is almost manageable, and then you can further partition that as you need. So not to claim that this problem is solved, but this is actually a beautiful place where there's an opportunity for research on indexing and clever methods for indexing in order for query processing to be faster. So again, in the database community, there's a huge amount of work on indexing, because if your index is very well designed, then at runtime you can do amazing things. So what is the appropriate index that would give you most of the way towards generating support sets for queries? I actually think this is a very doable agenda. Okay, the SPJ, it's something, training that is tricky for two reasons. One is, suppose I gave you the query, what is the place with the highest visitor count? Okay, you're talking about tourist attractions, and you want to know which one has the highest visitor count. And you have sentences like the Ibaraki Prefecture Museum of History has a visitor count of 93,000 people per year. Okay, so the core of what you need in order to answer this question is in the text. But what you need to do is you need to say, somebody gave me a query asking for the place with the highest visitor count. In order to answer that, I first need to extract visitor counts of individual places. So taking that aggregation query and translating it into a query that can be answered by extracting data from the database is the first challenge you have. And of course, the second one is to actually train the system to be able to extract it using the power of pre-trained models, but also fine-tuned for the relations that you care about. So that's the way we approach this. Now, I should say we actually created a data set. You've probably noticed by now in this talk that I'm raising a lot of questions and not giving all the answers. So in the natural language processing community, the way of doing that is you generate a data set so other people can do the work. So there is a data set called WikiNLDB. I'll give you a link at the end. It's out there with the ACL paper. And what we did was we generated a bunch of databases, relatively small, going from 25 to 1,000 facts, that we sort of know the answer. So the databases are in text, but since there's a mapping to facts in Wikidata, we know what's in there. Okay, so that's a data set that can be used to further research on neural databases. So again, we used data from Wikidata. They were verbalized using natural language generators, and we generate a bunch of queries, and you can go and play around with it. So I'm starting to run out of time here, but the point is that even on tiny databases, using our methods, which is Neural SPJ, Neural Select Project Join, plus the aggregation, we get much better results than the alternatives state of the art. And the more interesting result is that if you scale the database, and again, as a database guy, 1,000 seems is not really scaling, but it's more than 25. Given that the architecture is built for scale, there's reason to hope that this will scale to much larger databases. So our accuracy numbers actually hold up when we scale. The data is available. There are 2 papers about neural databases. One is in VLDB this year, which is more of a vision paper. The real work is in ACL, also a couple months ago. And I just want to end with a few challenges. that one should address when one talks about neural databases. So semantics are tricky, right? So if I told you that I work for Google, and then I told you that I work for Facebook, you would know that one of the facts has been, I no longer work for Google, okay? Because you can't work for two companies at the same time. You can if you're a professor, I don't know. But if I tell you that I like coffee and I tell you that I like tea, well, just because I like tea doesn't mean that I don't like coffee. So one of the challenges that we have in this whole area is to understand which facts override previous facts. And this is not so much of a database problem. Databases, you sort of build it into the logic of the system, but it would be nice for the NLP, for the natural language understanding, to realize that liking drinks is cumulative, but working for companies is, there might be a functional dependency there, as we like to say in the database world. One of the big questions here is for neural databases is great. You train the Neural SPJ for the relations you're interested in, but how much more training do you need to do when you're asking about relations that you've never seen before? And the answer is, well, I don't actually know. But the hope is, and some of our initial experiments confirm that hope, is that the patterns in language that talk about facts, even though they talk about different relations, there is a lot of repetition there. So after you've seen a bunch of relations, and if, for example, if you look at Wikidata relations, if you've seen a bunch of relations, then the amount of data that you need in order to train new relations goes down. Good. What I would like to see is a world in which we have training data for every, ample training data for any relation that people use in dialogue. Why not? We have Wikipedia. Why not have training data for every verb and every property we have in the world? Another thing that you have to be careful about is biases. Okay, if you're going to use these transformers to ask questions, well, you're going to get, you might actually get biases that are present in the data, and we need to protect against that from the very beginning. Let me stop there and take questions. Thank you. Assuming there's still anybody here.
Sure. We have a few questions in the chat. Some of them might be answered already. So, Tirish, you have a question.
Yes, thank you, Alon, for a very nice talk, a very interesting talk from all sorts of angles. My question, perhaps I wouldn't want it to be the first because it's a bit of a daft question, if you like. So in my thinking on the basic premise that you have unstructured data, essentially, yes, I remember your slide there with the few examples you had on the left-hand side, what John did and moved and so on and so forth. Is NoSQL to an extent capable of addressing this kind of thing? So I think the basic premise behind NoSQL was, although I admit I'm not using it as such in most of my work, but the basic premise was that you didn't need a database schema, so you could work with unstructured data, and you could work directly with the data without having to make a schema out of this unstructured data, right? Now, in your world, I guess you also have the benefit of the query being expressed in a natural language, because you were saying who lives in France, right? Rather than return all people whose country of residence equals France, right? But I was wondering where the delimiter lies, between NoSQL and neural databases,
I know that's a great question. So NoSQL does address part of the problem in the sense that I don't need to store the database in the data in a schema. So I can store anything. But now you're pushing the problem to the person querying the data. So, right? So if I want to ask who lives in London, then I need to think about the fact, okay, that if somebody moved to London, then I need to get that case. If somebody, I don't know, is working in all the different linguistic ways of saying that somebody lives in
Say
London.
that.
Now the burden, you can do that, right? So you have more flexibility. You don't have to store the data. You don't have to make these decisions when you store the data, but you need to be careful to make these decisions when you query the data.
When you query the data, right?
Yeah.
That's a good point. Thank you, Alon. Yeah, thank you for this great talk.
Thank you.
Any other questions? Thomas, I see you have a question in the chat here.
Yes, I wanted to ask about association rules. It was mentioned on one of the slides that they could be used, or they are used for superset generation. So I was wondering if you could maybe provide more details on that, because rules or rule learning is also relevant for this conference, or for the academic part of it.
Yeah, so maybe I should take that off the slide, because I was suggesting that they could possibly be used. I think we have not. I mean, you could use the idea of association rules to create support sets. So maybe if you have certain facts, they are typically associated, maybe they are typically joined with other facts. Okay, so now you can, in your index, you'll say, for example, if you'll say somebody moved to somewhere, somebody moved to a city, maybe it turns out that you often talk about where they work, or what company they work for. Okay, so that association, you get from looking at which facts were put together in transformers in order to get answers. So you can find that these, essentially what you're doing is you're finding which facts are typically joined. So facts that are typically joined, you may want to put in the same support set. So because if they're not in the same support set, you're not going to get the right result. That make sense?
Yes. Did you mean mining over the text? Because you can extract association rules from the text, or from the knowledge graph like Wikidata, because you could also extract rules with ILP-like approaches from directly from Wikidata.
Yeah, I mean, you can do both, right? At the end of the day, what matters is what questions people ask, right? So in Wikidata, you might have my birthplace and you might have my profession. How often do you ask, how many Israelis are computer scientists? I don't know. So it depends on, actually, you probably ask that a lot, but bad example. But there are certain facts that describe an entity, but they're very rarely combined in questions. What you really want to do is you want to mine how often these facts are combined, because that's the key to indexing. And I think that some of that has been already done. For example, in XML databases, right? People have looked at which kind of fact patterns people have followed frequently, and sort of created, I think they're called twig patterns, to index them together, right? And even in if you look back 20 years to auto tuning in Microsoft SQL Server, the idea was, okay, let's look at the queries that people ask and generate a set of materialized views that will make those queries run faster. So it's all based on the questions that you actually ask, because the representation of the data comes with a different set of principles than supporting queries. Representation is done for, I don't have to explain here, right? There are many principles that come into how you represent data and how not to represent data. But the queries give you sort of a very different perspective on your data. Does that make sense?
Yeah, okay. Thank you very much. That was very insightful. I did not realize the connection between analyzing query logs and formulating templates or patterns for association rule mining in knowledge graph, because otherwise there is this combinatorial explosion, but you could use the user queries to focus on a subset of association rules that you would like to mine. Thank you. That's an interesting point.
One more question from the chat, and then we can move to hands-on by Roman. About ambiguity. Ross asked the question about how do you address ambiguity in the approach? Do you address it? And if so, how do you address it?
So you would ambiguity in the question, ambiguity in the answers,
Probably
in the data?
both. Probably both.
That's a good question. Well, honestly, we haven't looked at that yet, but you can always say, John moved to London, and ask, does John live in London? Well, I don't know, maybe he moved out and you just don't know, or maybe move to London means that he's actually spending his half time in Paris and London, right? So language is ambiguous by nature. So I think the best answer I can give you right now is that when you give an answer, you also give the explanation. You show what is the fact in the database that led you to give that answer. And it's actually really important, because one of the weaknesses of language models today is that they hallucinate. If you ask a language model any question, it will never say no. It will always find some, if you say, Alon was a computer scientist in a particular year. No, sorry. Any sentence that you give it, if you give it a mask, okay, something to fill in, it will always fill something in. Okay, it'll never say no. There's no way to fill this in. Okay, just because of the paradigm that there's always something in the text that the probability of that something being the right word in that sentence is more than 0. Okay, and if it's more than 0 and more than all the other options, it's going to be there. Now, that's bad, right? Because that means that the language model is making stuff up. So in the case of neural databases, at least, what you can do is you can force the system to show you exactly the facts in the database that it's relying on. Okay, and that at least, and if there's an ambiguity there, then the human will already realize it, right? So if there's some subtlety that then the human will realize that the system didn't understand correctly. But that's the best answer I can give you right now.
Okay. I hope that answers the question. There was a question by Roman Bauer. Is it still active? Yeah.
Yeah, sorry, I was getting tired from holding my hand up. Yeah, thanks a lot for this very interesting talk, Alon. As a neural computational neuroscientist, I was particularly, of course, interested in the neural part of this. Could you maybe elaborate more on the neural perspective and the terminology? Why is it exactly called neural? And also, how do you envision this to be applied for other modalities other than language? Like, I suppose I think you mentioned also that this could potentially be applied for images or so.
Yeah. Why do we call this neural databases? It's kind of a cool name, to be honest. Okay, but really the reason is that the core operator in the database is using neural techniques. Okay, and so we're not doing scans and selections and projections the way database people do. We're actually breaking we're decomposing the problem, and at the leaves of the tree, we have a bunch of neural nets running. So it's a real paradigm. It's really different than the existing paradigm. Now, again, I haven't done it yet. We haven't done it yet, but you have very powerful visual query answering systems that can tell you stuff about images. They can tell you, is there a desk in the image? Is there a person? Is the, even sometimes it can tell you what is the person doing. So there's, or you can imagine a query which is, how much does the bag or the bag that the woman is holding in the photo, how much does it cost? Okay, so you can get the bag, and then you can do, you can find the price. So actually, the vision world has made amazing progress using neural techniques over the past few years. And so I think the beauty of neural databases is they essentially they take the latest and greatest in all the neural advances, and they just make them scale to database queries. So we're not trying to make to advance the neural techniques. We'll just take the best that exists there, but we're just adding another layer over the neural techniques that enables you to answer a lot of questions over that multi-modal data. So that.
Thank you.
What are transformer models you use? Question from Jürgen Angele.
The transformer that we used was a T5.
Okay.
In the NLP world, that'll be obsolete in about 3.5 months. So, don't quote me on that. Jürgen.
All right. No more questions.
Alon, just one generic question. Let's imagine you give similar talk in 5 years to the same audience. How do you expect you would answer some questions about ambiguity or similar difficult questions?
Well, so in 5 years, I would expect, so we developed neural databases as sort of a standalone system. I actually think that existing database systems can actually benefit from having a neural component. So if you look at the development of database systems over the years, people started with a new idea, and then somehow it migrated in some form into existing database systems. So I expect that in 5 years, I don't know how long it's going to take, but at that point, you'll have a neural operator in a traditional database system. So that's one thing. My real hope is that the paradigm. I'm very troubled with the current paradigm of machine learning, which is you have one question you want to answer and you build a model. I want that paradigm to be. I want the paradigm to shift to there is a domain that we care about. And now we're going to build something where I can ask different questions about this this domain. Okay, that's a different way of thinking about machine learning. And I'm not to say that people aren't already doing that, but they're focusing on few shot and zero shot learning. But the fact that a machine learning model is basically answering a query about data, and now you want to be able to make that query system more flexible in the variety of queries. They're focused on the variety of data and getting everything that you can out of the data, but the machine learning community doesn't think about queries and the world of changing and drill down and stuff like that. That's what I want. That's what I want to change.
It's interesting that you mentioned this, because yesterday we had a presentation on both conferences from young researchers from Belgium, and they had just very unusual approach. We have business rules that describe our problem domain, and you have one query, and you try to address this as a goal, forward chaining goal. And they considered, what if I just have name of this query, and can I find knowledge inside my rules to ask right questions? So they also talking about set of questions in right sequence with minimal path to find the answer. It's not always one answer, but it's a set of answers and automatically discovered from already existing rules. That's the opposite direction for rule engine. It's kind of back to backward chaining. So this is interesting that you mentioned the same.
I think machine learning is getting to a stage where it's getting mature, but it's also still at its, in terms of its usage in industry, is still very much, we're still figuring it out. Yeah.
Okay, thank you very much.
Thank you.
Any other questions? Okay.
Okay.
Thank you, Alon, and hopefully we will really see you in a few years again. Stay in touch.
Thank you.
Thank you very much again.
Thanks for having me.
Thank you, Alon.
Thank you.
Bye.
Bye.